Okay, hi kids. Tonight we're looking at 4.3, connecting f prime and f double prime with the shape of the graph of f. Just going to review a little bit about what we did in the first part of this lesson. So you'll be able to use derivatives to analyze properties of a function to determine the intervals of increase or decrease, and then both second and first derivative tests for local extrema is something that we'll work on. And then intervals of upward and downward concavity, points of inflection, and identification of key features of functions and their derivatives. So we started out with the first derivative test for local extrema. And if you look at the notes on the right-hand side, just taking these rules and kind of making them a little bit simpler, just with the layout with the number line. And so we look at a critical point. We have a local max in the conditions where if f prime goes from positive to negative, and the function is continuous, then we have a local max there. If f prime goes from negative to positive on the function and the function is continuous, we have a local minimum. And then if f prime goes from positive to positive or negative to negative at c, then we have no local extrema. Then we also discussed how we have at a left endpoint or a right endpoint, we may have a local max or a local min in that neighborhood. And those two are, though highly contested at one point, we've come to accept in the world of mathematics that they are considered local or relative max or mins. So then we talked about using the first derivative test on a function. This is a cubic function. So our first step is that we said we would take the derivative and then find the critical numbers. So when we found the critical numbers, we put them on a number line, and then we tested on a number line. So I'm going to make this step 3 here, put that out in the bracket here. So I've got a graph up there for you already, but always wise to consider the behavior of a graph first. So in blue, you see that as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity. So there are no absolute extrema with this graph. So we take the derivative, find the critical numbers, and it matches up with the graph that I've provided for you to kind of see where they are. Though, as I said before, you may not have a graph. You may not have a graphing calculator, and you may have to do all the algebraic work that goes along with the first derivative test. So then I'm going to take the factored form of the derivative that you see above the number line, and with that, then I plugged in test points on the intervals divided by the critical numbers, -2 and 2. I chose random numbers on the intervals, -3, 0, and 3. You can pick any number on the interval, but generally for ease of arithmetic, we pick numbers that are easier to compute. So once we do that, we can see that the function is increasing, then it goes to decreasing, then it goes to increasing. And so we can see that we have a local max at -2 and a local min at 2, which matches up again with the graph that you see. And then once we get our information, then going to find f of 2 and f of -2 to get the values -21 and 11 for our local min and max. And so what we would say is that we have a local maximum value of 11 and a local minimum value of -21. Again, no absolute extrema on this particular graph. Okay, so that's example 1. Example 1b, that was 1a. 1b, we have the function where g of x is equal to the quantity x squared minus 3 times e to the x. So we, again, in the first step, we took the derivative. In the second step, then evaluating the derivative at 0, finding the critical numbers. And then the third step, putting the information on a number line where we have the critical numbers, -3 and 1 on the number line. We have test points of the intervals, -4, 0, and 2 on those intervals. And you can kind of see that from -infinity to -3, the function g is increasing. From -3 to 1, the function is decreasing. And from 1 to infinity, the function g is increasing. So increasing, decreasing, increasing, you can see we have a local max at -3 and a local min at 1. Now, what we did is we looked at the end behavior of this graph also, because we did get the local max and the local min and put the points in. And you can see that I have it in exact form on the graph, but I rounded to 3 decimal places. And then as it turns out, saying that the limit as x, let me push this down here, we said the limit as x approaches -infinity of g of x, that was 0. and then the limit as x approaches infinity of g of x, that's going to be infinity. So we can see the behavior such that we know that the local minimum value that we see at the bottom of the graph, that is the lowest value, and the graph is never going to come back down to anything lower, so that we actually have an absolute minimum on the graph of negative 5.437. Okay, so we have our information there. Then we moved on to that was our second first derivative test problem. Then we talked about concavity. And a note of caution when discussing this is that you have to talk with the specificity about the functions. So if y prime decreases, then y double prime is less than 0. If y prime increases, then y double prime is greater than 0. And let me page forward. We kind of did these diagrams to note the tonality of the situation when f is concave up, f double prime is greater than 0, and y prime is increasing. And then when f to the right, then when f is concave down, then f double prime is less than 0 and y primes are decreasing. Now remember this, we see the y primes with the tangent lines that we can draw on the graph. Okay, so then we went to look at the concavity test, and we will use that in our next example. So again, with Mr. Smiley and Mr. Frowny, concave up, concave down. And then we did the concavity test with our example, y is equal to x squared. So we took the derivative, we got y prime, our first derivative, and we got y prime is equal to 2x, and then y double prime is equal to 2, and we said that was greater than 0. Now keep in mind, the question here that we addressed is that we're using the concavity test to determine the concavity of the given functions on the given intervals. So with this particular question, we found out that y double prime is equal to 2, which is greater than 0. So then we can conclude that y is concave up everywhere, and that's on the interval from negative infinity to positive infinity. So then we can conclude that it's concave up on the interval from 3 to 10. I think that's what it was saying. Okay. And then on the next example, we have y is equal to 3 plus sine x, and we're only talking about the interval from 0 to 2 pi. So with this problem, we said, okay, well, the first derivative is given, it's 0 plus cosine x. And then the second derivative, which we'll use in this problem, is negative sine x. So here's the first step. And now we've got to get the second step, which is the second derivative. And then we set it equal to 0. Now what we're doing is we're looking at possible sign changes. Okay, possible sign changes. So that occurs at 0, pi over 2, and 2 pi. 0, pi, and 2 pi. So we put those numbers on the number line, and I'm going to just lay them out like this because we are only on the interval from 0 to 2 pi. So when we do that, we find out that the second derivative is equal to negative 1 when we use the test point of pi over 2. And I picked pi over 2 on the interval at random, but it was easy to say, all right, it's pi over 2. Therefore, on the interval from 0 to pi, the second derivative is going to be negative because our test point pi over 2 was negative. Therefore, on the interval from 0 to pi, the derivative will be negative. Then, in addition to that, we have a test point of 3 pi over 2. When we plug that in, we get the negative of negative 1, which is then going to be a positive. 1 is positive, so it's the derivative y double prime is positive on the interval from pi to 2 pi. So then we can state on these intervals, the first interval, y is concave down, and on the second interval, y is concave up, and I have stated the intervals here. And if you look at the graph that you see, the graph of y is 3 plus sine x, so 3, it moves the graph of sine x 3 units up, and then y2 is down below, and I have it highlighted on the intervals where the graph is concave down and concave up respectively. So there you have it. There it is. There you go with that example. And now let's do a quick one on points of inflection. A point where the graph of a function has a tangent line and where the concavity changes is known as a point of inflection. So you can look at a graph and you can say that the graph goes from concave up, and it's not going to really matter, concave up to a point and then concave down, concave up to concave down. Then we know that this point is a POI, a point of inflection. It can also go from concave down to concave up, concave down to concave up, and then this would be a point of inflection. Then you can also have a situation, let me make it like this, so you can come, it's concave up, and I just want to illustrate this with one, so, and then concave down looks something like this. So it doesn't always look like a U shape. In fact, where you have concavity here, you have a slope at the point of inflection. But for this last one, for the point of inflection, you may have a vertical tangent where the slope is undefined. So there's always that looming out there. But it's a point where the graph of a function has a tangent line, and where the concavity changes. And that's a point of inflection. So this will be the last one on this video, and then I'll have to start another one. But for this, the first step is we're going to find where f double prime is equal to 0 or undefined. And then the second step, we're going to do the concavity test on a number line. And if the sign change, if there's a sign change, then that's going to be a point of inflection. So step 1, so we have f prime first. So f prime is equal to, we have an e to the u form, remember, so I'm going to write this down as the derivative will be an e to the u times du dx form with working with exponentials. So in this case, u is equal to negative x squared, and du dx is equal to negative 2x. So we get f prime of x is equal to e to the negative x squared times negative 2x. So I'm going to rewrite this, and as it turns out, I'll probably be using this again, so I'm going to rewrite it with the negative 2x out front, e to the negative x squared. So there that is. Now we're going to go ahead and we're going to get the second derivative. So we have f double prime of x is equal to, now notice the first derivative is now a product. So we're going to say first is negative 2x. Remember, we're using product rule to always be aware. There's our first factor, and then here's our second factor. So then I have first der second, so I'm going to take the derivative with respect to x of our e to the negative x squared plus second e to the negative x squared times the derivative of the first, which is negative 2. Okay, I'm going to simplify, but let me get this worked out here. So I have f double prime of x is equal to negative 2x, and I've got the derivative of e to the negative 2x, which is the first derivative, right? So it's going to be negative 2x e to the negative x squared, and then I've got plus e to the negative x squared. I could rewrite this too, just for a little bit ease here. So it would be minus, let's put a minus in there, minus 2e to the negative x squared. And so I'm going to factor out the common factor now of negative 2e to the x squared. So I get, well, I think I might leave the negative 2 in there. I'm going to say f double prime of x is equal to, I'm going to factor out the e to the negative x squared, and then I'm left with 4x squared minus 2. Okay, and so now what I'm going to do is I'm going to set the second, I want to find out where f double prime, this is really step 1 on the steps that I gave on the side, so then I'm going to say, where is this equal to 0? And so you can kind of see that this is equal to 0 when, now if you look at it, I'm going to put this over here just to save some space. when e to the negative x squared is equal to 0, or when 4x squared minus 2 is equal to 0. E to the x squared is never equal to 0. In fact, e to the negative x squared is always greater than 0. So, and then here we have x squared is equal to 2 over 4, which is 1/2, right? So let me put 1/2 there. So 4x squared is equal to 2, and then x squared is equal to 1/2. And so we get x is equal to plus or minus the square root of 1/2. We very often write that then as x is equal to plus or minus root 2 over 2, like that. Okay, so now what we have here are possible POIs. Okay, possible POIs. Okay, go like this. Okay, and I'm going to make this just a little bit smaller. Whoops. You know, the video is getting kind of long here. So there we go. There. I'm going to put that over like that. Okay. So, and you can kind of see on the graph that I would want to know what the value of this is. And you can see you have some symmetry with your x's. So remember, this is 0.7071, so we have plus or minus of that. So you see where we have the 1 mark there, and there seems to be another point over here, right? So these x values are root 2 over 2, and then of course we could find the y value. And here we have negative root 2 over 2, and then the y value. So the graph, it appears that we do have that situation. But what we're going to do is we're going to go through the whole enchilada using the concavity test first. Okay, so we'll use the concavity test 3. So knowing, oh, by the way, possible POIs, if you will. So 3, I'm going to do a number line again, because that is kind of an easy way to test. And so when I do the number line, I'm going to put the 2 values on it. And now remember what the value is. So I'm going to say negative square root of 2 over 2, and we know the value of that. And then in between, oops, hold the phone, Dolly. So then I've got positive square root of 2 over 2. And the test points, see, I'm going to do the same thing. It's almost like the first derivative test, but not really. I'm going to use negative 1 here and 1 there. Okay, so I'm going to test on the number line. Okay, when I test on the number line using negative 1, 0, and 1, it's because using 0.7071, I can say that 0 occurs between negative root 2 over 2, and then negative 1 is to the left, 1 is to the right of the respective negative root 2 over 2 and root 2 over 2. Okay, so now what I'm going to do is I'm going to test the derivative. So remember, here's your second derivative, f double prime, in this case is e to the negative x squared, 4x squared minus 2. And so if I put these 2 factors, I'm just going to leave it as 2 factors. You really could factor 4x squared minus 2, but it's kind of easy with the values that I have. The first factor is always going to be positive. Now, if I put negative 1 in, I'm going to get a positive. So negative 4 times negative 1 squared is 4 minus 2, positive. So here we have f double prime is going to be greater than 0. If I put 0 in here, I'm going to get a positive times a negative. So now I know my second derivative is negative. And if I put a 1 in, I get 4 times, remember, e to the negative x squared is always positive. If I put 1 in, I'm going to get 4 times 1 squared minus 2, which is 4 minus 2, which is positive. So I get a positive times a positive on the last interval from root 2 over 2 to infinity. So let's make our conclusions. So now we know that f is concave up on the interval from negative infinity. I'm going to go ahead and write this. I kind of missed this on the last couple problems. To negative root 2 over 2. and it's concave down. Remember, f is the function, is concave down on the interval from negative root 2 over 2 to positive root 2 over 2. And then the graph of f is concave up from root 2 over 2 to infinity on those intervals. So that means that since the function is continuous, so we can make a conclusion, since f is continuous, I guess I should say since f is continuous, there exists a POI, point of inflection, remember, at, and these are the points, at, let's say x for this one. This video is getting kind of long. X is equal to negative root 2 over 2, and x is equal to root 2 over 2. There exists points of inflection. Let's make that plural then. Okay, and so we have those two. Now, to get the points on the graph, then we would put those values back into the function. So we have POIs at root 2 over 2, root 2 over 2, 1 negative, 1 positive, and then the function of root 2 over 2. Usually we just go back and get the value for that, and I'm going to leave that up to you in this case. Or do I have them? I think I have this is the decimal equivalent of the y value, 0.6, but we would just get an exact form. So that is rounding up this problem, finding points of inflection, where we find the second derivative is equal to 0, do a concavity test, and look for a sign change in look for if the sign changes in y double prime, or in this case f double prime, then we have a point of inflection as long as the graph is continuous. So I'm going to let you go then and start with the second derivative, the next video, going over reading the graph of the derivative. Okay, so I'll see you on the flip side.